All right, welcome back to college algebra. Oops. I want to share just the application window. Here we go. There we go. That's perfect. All right. So today I want to take a step back from logarithms and we're going to talk about just functions in general again for a bit. If I tell you I want to solve an equation like 2f of x plus 3 equals 7, if that's the equation I'm trying to solve, then of course I can subtract 3 from each side and have 2f of x equals 4. And of course I can divide each side by 2 and get f of x equals 2. But that's as far as we can go without knowing something specific about f of x. Okay, so I can't divide by f, I can't subtract f. Remember we talked about this in person. We're going to treat f of x like an atom. It's one thing, it's not divisible, it's the symbol for the output when you put x in the input of the function f. So this is just one symbol, it's the name of the output. Now, I'd like some way to recover the input from that. So when I say this is the output, I mean, let's picture f as being a machine on an assembly line. So we've got some automatic conveyor belts here. When I put x into that function, a 2 is going to come out of that function. But I want to know what x did I put into the function originally to get that 2 out of there. So what I'd like to be able to do, and for some functions this is possible, for some functions it's not, but the ideal situation is if I could just kind of run this whole thing backwards. And say, when I move 2 back into f, if I run this whole belt backwards, if I put 2 in, I should get x out. And this machine run backwards, I write it f with a little superscript -1. Now this is not an exponent, it's just notation. We pronounce it as f inverse. So this whole thing, f inverse, is the name of this backwards function. Question? Go ahead. If you're talking, I cannot hear you. You could also type your question in chat. So while we're waiting on that question, I just want to clarify again, this -1 here is not an exponent. So this is not the same as 1 over f of x. This is a different thing entirely. This is f of x, but running in full reverse. So I would say, over here, I'd say f of x equals 2. And here I'd say f inverse of 2 equals x. This is like saying x is the number I'd have to plug into f to get 2. When I write f inverse of 2, I'm asking, what number do I have to plug into f to get this 2? And the answer is x. So far, so good. All right. Oh, okay. No worries. Thanks for clarifying, Beyonce. Yeah, if your microphone's not working for whatever reason, you can always type your question in chat. So, in other words, now this is not always possible. Not every function can be run in reverse. Not every function has an inverse. So we'll be talking today about which functions do and which functions don't. But if there's an inverse, So right here I'll write, if F inverse exists, then we can finish this problem by writing x is F inverse of 2. So I haven't really written anything new. This is like changing an exponential expression to a log expression. I haven't got any new information here. I'm just rewriting this equation in a different way. But it's a way that allows me to put x by itself. I'm saying x is whatever you have to plug into F to get to. So this is a symbol for x. Then if we know what function F is, then we can find a formula for F inverse, plug 2 into it, and actually get x out. So here's an example of a function that has an inverse. Maybe this will make things a little clearer. I'm going to say g is the function that converts degrees Fahrenheit into degrees Celsius. And if that's the function that g is, then I actually do know the algorithm for g. It turns out that I would write g of x equals 5/9 of x minus 32. To go from Fahrenheit to Celsius, first you have to subtract 32, and then you have to multiply by 5/9, because degrees Celsius are a little bit wider than degrees Fahrenheit, but they also start at freezing is 0 instead of freezing is 32. So for example, if I have the boiling point of water, this is a good one to test us. I know that 212 degrees Fahrenheit is the boiling point of water. And I also know that Celsius is a little more sensible. It sets the boiling point at 100. So if I plug 212 into this function, I'll get 5, it's a terrible 5. 5/9 of 212 minus 32. So first I do what's in parentheses. This is 5/9 of 180. And then 180 divided by 9 is 20, multiplied by 5 is 100. So this function is working for boiling, and if I really want to be sure, make sure it works at 2 points. The temperature at which water turns into ice is 32 degrees Fahrenheit, but it's 0 degrees Celsius. So if I do g of 32, I'm going to get 5/9 of 32 minus 32, which is, of course, 5/9 of 0, which is 0. Okay, so this works at 2 different points, so now I'm pretty sure this really is the function that converts from Fahrenheit to Celsius. And specifically, actually, let me get rid of this line. I don't want this here. So what I did to go from Celsius to Fahrenheit, was first I subtract 32, and then I multiply by 5/9. So if I want to undo those steps, let me put it this way. When you get dressed in the morning, one of the last things you do is you put on your socks and then you put on your shoes. So I'm going to think of these as being like our socks and our shoes. The reason I'm saying that is then when you get home and you take your shoes and socks off, you can't take your socks off until you've already got your shoes off, because your socks are inside your shoes because you put on the shoes last. So if I want to undo these steps, first we have to take off our shoes, and then we have to take off our socks. So think of it like socks and shoes. The last thing we did is the first thing we undo. So to get rid of a 5/9, I'd multiply by 9/5. And that's going to get me up to 180. So I'm undoing that multiplied by 5/9. I'm changing this 100 back into a 180. I'm doing each step in reverse to get back to the starting point. Put on the socks and shoes. Now we took off our shoes. Now we can take off our socks. So to get rid of subtracting 32, I'm going to go ahead and add 32. So 180 plus 32 is 212. and we're back at the original number. So by following each of the steps that made up the function in reverse, I've undone the function. So let me write out what we did. What I'd say is first we had x, and it looks like then whatever we plugged in, so in this case x would be the 100. We multiplied it by 9/5, so I'm going to multiply it by 9/5, and then we added 32. So those are the two steps that undo g, so I'm going to say this is called g inverse of x. And the important thing is, the way I'm understanding this is g inverse undoes g. That's what makes an inverse function an inverse function. That's the characteristic that we're interested in here, is that they undo each other. So for example, if it is, let's say it's 68 degrees Fahrenheit. Say it's a cool morning here and it's 68 degrees Fahrenheit, but I'm trying to tell my friend in Germany what the temperature is. Well, they only understand Celsius over there. So if I want to convert that Fahrenheit to Celsius, I can put it into G. G of 68 is 5/9 of 68 minus 32. Whoops, that should be in the parentheses here. So 68 minus 32 is 36. So this is 5/9 of 36. Nice thing is that's divisible by 9. 36 over 9 is 4, times 5 is 20. So I could tell my friend in Germany that it is 20 degrees Celsius. And then check this out. If I plug that into G inverse, I'm going to have G inverse of 20 is 9/5. So now I'm using this formula, the one that takes off the shoes and then takes off the socks. So G inverse of 20 is 9/5 of 20. And then on the outside, plus 32. Well, 9/5 of 20 is 9 times 20 over 5. That's 9 times 4, which is 36, plus 32. And 36 plus 32 is 68. So if I know the inverse function, I can recover the original data. In this case, if G converts degrees Fahrenheit to degrees Celsius, then G inverse converts degrees Celsius back to degrees Fahrenheit. One more cool property with this example that I want to show you is, now let's say my friend in Germany says es ist 35 degrees Celsius, and I know enough German to know that that means it is 35 degrees Celsius. So he's just told me it's 35 degrees Celsius. Very hot day over there in Germany. Well, if I want to know what that is in Fahrenheit, I can go ahead and plug it into G inverse. G inverse of 35 is 9/5 of 35 plus 32. So I've used the formula for G inverse again. Well, 9/5 of 35 is 63. So that's 63 plus 32. Add those together and I get 95 degrees Fahrenheit. But what's really interesting is if I put 5 into G, the formula for G was 5/9 of x. So in this case, 95 minus 32. So first we subtract 32, we get 5/9 of 63. And then of course, 5/9 of 63 is 35. So what I'm showing you here is that this process, yes, I know the mic is off. This process works both ways. So G inverse undoes G, and G undoes G inverse. These always go together. If G inverse undoes G, then G undoes G inverse. In other words, I'm not really going to say G inverse is the function that undoes g, I'm going to say these two functions undo each other. So inverse functions always come in pairs. The inverse of your inverse is the original function. So, whoops, don't know how that got on the screen there. Don't need that anymore. Let's go turn that off, can I? Nope, that's not going to do it. Neat. Okay, well, I guess that's just stuck there now. Oh, okay, there it goes. It's a toggle button. Sorry, class. G undoes G inverse and G inverse undoes G. So inverse functions come in pairs. Any questions so far? All right. What I'm saying is, let's think about the implications of this for a second. If I put G of X in G inverse, I get X back. So in other words, what I'm saying is if I take G inverse and I put G of X into it, I get X back. So I'm putting G of X into G inverse and I get X back. This is from 3.5. Function composition. You remember in 3.5 when we had that O symbol to plug one function into another function? This is that. If I compose a function with its inverse, I get the X back. So if I put G of X into G inverse, I get X back. Like if I put, where was it? 20 was G of 68. So if I put G of 68 into G inverse, I get 68 back. I could write this as I put G of 68 into G inverse, and I get 68 back. Put this where it goes here. Because G of 68 was 20, and G inverse of 20 was 68. And the thing is, this works in the other order too. Since G and G inverse are inverses of each other, I can write G inverse of G of X equals X, or I can write G of G inverse of X equals X. Whichever order I put them in, that's the inverse. So when I say these two functions undo each other, this is how I'd write that mathematically. So we're going to use this as our definition of inverse functions. If the functions undo each other in both orders, you've got a pair of inverses. This is the mathematical statement of that definition I gave you in English a little while ago, where I said G inverse undoes G. So this is the mathematical version of this statement. All right. I also want to draw a little diagram with the domains and ranges here. So if this is some number x, and let's say this is the function g, so that's going to turn x into g of x. Here, let's instead of calling it g of x, let's call it y. So I'm saying g of x equals y. Well, g inverse has to undo that, so I would have to say g inverse of y equals x. It undoes the process g did. So if g turns x into y, then g inverse turns y into x. So g inverse is the function that goes this way. They undo each other. And that means if I take x and I plug it into both, g inverse of g of x, first I go to y and then I go back to x. And if I take y and plug it into g inverse and then plug that answer into g, I'm going to get y back. So it's just a cycle. If I take x, I plug it into one and then into the other, we're back at x. If I take y and I plug it into one and then into the other, we're back at y. So that's these two parts of the definition here. But another consequence of this is if x came from the domain of G, then that means y must be in the range of G. But another thing that's true about these two ovals is that if these two functions are gonna undo each other, then whatever came out of G has to be able to go into G inverse. So this is also the domain of G inverse. And whatever comes out of G inverse has to be able to go into G to get back to where it started. So X here is also the range of G inverse. So the domain and range have switched places. G takes something out of this bucket and puts it into this bucket. G inverse does exactly the opposite. It takes something out of the second bucket and puts it into the first. So the domain of G, the bucket that G takes out of, is also the range of G inverse. It's the bucket that G inverse puts things into. And over here, this oval, the range of G also has to be the domain of G inverse. So the domain and range have just switched places. Yeah. Any questions at this point? Well, if not, then what I want to do next is we've done a lot of algebra. We've done a real-world example. We've got a domain and range diagram. I want to show you some geometry now. So let's go ahead and graph a function that has an inverse. Let me say that h of x, we're going to let that be x cubed. Now I know what the graph of x cubed looks like. Remember, this is one of our toolkit functions. It's this swoosh shape here. That's a pretty good graph. So this is x cubed. And so if I say h of x is x cubed, or I'm saying, then this is the graph y equals h of x. Let me see here. What's a point on this graph? How about 2, 8? Because 2 cubed is 8. So 2, 8 is on the graph. In other words, I'm saying since h of 2 equals 8, 2, 8 is on the graph. These two statements, h of 2 equals 8 and saying 2, 8 is on the graph, mean exactly the same thing. That's the definition of the graph, is it's all the points where if you plug the x in, you get the y as the output. So saying that this is a true statement about the function is the same as saying this is a true statement about its graph. So h of 2 is 8. Well, that means if the inverse function undoes it, in this case, the inverse function, what undoes a cubed, would be, does anybody know? That's all right. What undoes a cubed is the cubed root. So h inverse of x is the cubed root of x. Because if I plug 2 cubed equals 8, then for example, the cubed root of 8 equals 2. And that, of course, h inverse of 8 equals 2. That undoes h. So if I put the output into h inverse, I have to get the input back. So it undoes this process. We're running the factory line in full reverse. So when I say h inverse of 8 is equals 2, when I said h of 2 was 8, that meant that 2, 8 was on the graph of h of x. But if h inverse of 8 equals 2, then that means that 8 comma 2 is on the graph y equals h inverse of x. So here's a point 8, 2 that has to be on that graph. And as a matter of fact, if I say h of x equals y, that's the same as saying that xy is on the graph y equals h of x. But if I say x is y, and h has an inverse function, that means that if I plug y into the inverse, h inverse of y, that has to be x, and that means that yx is on the y equals, whoops, h inverse of x graph. So just like the domain and range changed places, the x and y coordinates have changed places. Now this point has to be on this graph. So if 1, 1 is on this graph, then it's on the other graph. 2, 8 is here, 8, 2 is there. 3, 27 is here, 27, 3 is there. 4, 64 is here, 64, comma 4 is there. The x and y coordinates are just changing places. If I want the x and y coordinates to change places, well then what that means is, take a look at this. Here's the line y equals x. If I reflect over this line, I'm changing every x coordinate into a y coordinate and every y coordinate into an x coordinate. So this is going to be the graph of h inverse. Actually, we know what this graph looks like. It's the cubed root. So we can check our toolkit functions page and see it looks like this. But yeah, take a look at that. If you put a mirror right on this blue dotted line, it's the reflection of the black curve over the mirror, is the green curve. And that's true of any inverse functions because of this relationship down here. Since the x and y coordinates change places because it undoes the other function, since the x and y coordinates are changing places, that's the same thing as reflecting over this line. So this is what the graph of an inverse function looks like, is you reflect over this diagonal line, and now you have a new graph. Let's see here. Now, just as a warning, not all functions have inverses. I know I said this already, but now I'm ready to give an example. Not all functions have inverses. And here's an example of one that does not have an inverse. If I say that f of x equals x squared, this is an example of a function with no inverse. So I know that f of 3 is 3 squared is 9. So f of 3 is 9. And I also know that f of negative 3 is 9. And that's because negative 3 squared is positive 9. So both of these turn into a 9 when I plug them into f. And the problem is, well then, if f inverse exists, what in the world is f inverse of 9? 3 or negative 3? There's no way to, it would have to be both. For it to undo f, it would have to turn it into 3 sometimes and negative 3 other times, but there's no way for it to choose. Whenever I have a function, every input has to make only one output. That's what makes it a function and not a relation. So because f inverse would have to have 2 outputs for one input, it is not a function. We can see that on a domain and range diagram. If I draw this oval, here's 3, and here's -3 in the domain. F turns both of those into a 9. So if I'm trying to undo that, I'd have to pick, does F inverse turn 9 back into 3 or back into -3? It can't be both, but by the definition it has to, so we just say F inverse doesn't exist. The way I'm going to label this diagram is I'm going to say F is not 1 to 1. 1 to 1 would mean one output comes from one input. Every input goes to one output. This F has 2 inputs going to one output, so we'd say F is 2 to 1. But it has to be 1 to 1 to have an inverse. So I'm saying this doesn't have an inverse. Another way to understand why this doesn't have an inverse that I think is even more intuitive is, since I showed you that graph before, let's take a look at the graph of F. So here graph y equals x squared. And I said, if the inverse exists, since the x coordinates and the y coordinates change places, like they did up here, since the x coordinates and the y coordinates change places like they did up here, I can do a reflection over this line y equals x. This blue dotted line is going to be our mirror to make the graph of the inverse function if it exists. So I'll scroll back down to y equals x squared. Let me draw my blue dotted line. This is the mirror I would have to reflect over to make an inverse function. This is the y equals x mirror. So I reflect this black curve. Imagine a mirror right here. Imagine this is a piece of paper and the blue line is an axle and you're flipping the whole paper over on the axle. So here's the result. This is what you'd see in the mirror if the mirror was y equals x and you were looking at y equals x squared. This is the mirror image of that. So this is the inverse function if it exists. Well, there's a very big problem with this red curve. The red curve is not a function. Why? Because it fails the vertical line test. If I draw a dotted line through it, a dotted vertical line specifically, I'm seeing I have one input with 2 different outputs here. So since one input has 2 outputs, it fails the VLT. So I want to know, is there a way to check that black curve without doing all of this work? And the answer is absolutely there is. The fact that this red line crosses the red curve twice means the red curve isn't a function. So if I didn't want to have to draw the red curve, what I could do is reflect this line over the blue dotted line, over the mirror y equals x, to make this black line. So this is the reflection over my mirror. That wasn't a very good dotted line. You can see the idea, right? I call this black dotted line the horizontal line test. So since this horizontal line hits f at 2 different points, f is not 1 to 1. So a function is is 1 to 1, passes the horizontal line test, and has an inverse. All 3 of these statements are equivalent. So if one is true, then all 3 is true. If one is false, then all 3 are false. If it's 1 to 1, if each output comes from only one input, then that means it must pass the horizontal line test and it must have an inverse. If I know it has an inverse, then I know it passes the horizontal line test and vice versa. So all three of these, there are three different ways to define it in terms of three different ways of looking at it: a domain range diagram, the algebra, or the geometry. But these are the three equivalent statements in those three different domains of knowledge. If you know one is true, you know all three are true. And if you know one is false, you know all three are false. So for example, this line, this graph y equals x cubed. Come on, scroll. There we go. I can see that wherever I draw a horizontal line, it's going to intersect this graph only once. So if I draw a horizontal line through up here, it's only going to touch the graph once. Wherever I put a horizontal line, it's only going to touch the graph once. And that means if I flip those lines over y equals x over the blue mirror, every vertical line is only going to touch the inverse once, and that means the inverse really is a function. So if the inverse really is a function, that means h has an inverse. I can't say h has an inverse if the line that would be the inverse isn't a function. So that's why I would say this function f here, it doesn't have an inverse, because the curve that would have to be the inverse is not even a function. So the horizontal line test is going to be how we determine if a function has an inverse, if we have the graph. All right, so that is the geometry of inverse functions. Let's go on, unless there's any questions. All right. So then my third and final task in section 3.7 is to ask, if there is an inverse, how do I find it? And here's what we're going to do. For that Fahrenheit to Celsius function, I just said, well, you put on your socks and then your shoes, so we'll take off our shoes and then our socks. This is just going to be the algebraic extension of that principle. And what we do is we set y equal to f of x, and then, so I'm going to put in the equation here. I'm going to put in the algorithm for that function, and then I'm going to solve for x, and whatever solution I get x into, that has to be f inverse of y by definition. So those are the steps. It's going to be easier to see what those steps are if we do examples. So I've got 3 examples prepared for you. Here's an easy one to start with. If I said that f of x was equal to 3x plus 2, I could figure out the inverse with the shoes and socks method, since there's only 2 steps to this function. First we multiplied by 3, and then we added 2. So my guess is, if I'm going to make the inverse, to get that inverse, first I'd have to subtract 2, and then I would have to divide by 3. So I'm guessing that's going to be the equation for the inverse. Let's see if the algebra holds up. So step 1, I'm going to set y equal to the equation for f of x. Step 2, I'm going to solve for x. So I subtract 2 from both sides, divide by 3. And now x is by itself, but I know that if y was f of x, then I know that x is f inverse of y, because f inverse undoes f. So up here, if y was f of x, if I switch that order around, x has to be f inverse of y. If I plug this into the inverse function, I have to get that back. So I'm going to say that's step 3 is I say x is f inverse of y. And then this last step is a little bit goofy, but it's something they like to have you do, is we're going to change the name of the variable, because I want x to be my input function. So instead of writing f inverse of y as y minus 2 over 3, I'm going to write f inverse of x is x minus 2 over 3. I haven't done any math in this step. I'm just renaming y to x so that x can be my input and y can be my output again. So the meat of the problem was step 2. Step 1 was setup, and step 3 was some shoe shine on the finished product, but step 2 is where all of our work gets done. Is we say y equals f of x, and then we solve for x. And this will work for pretty much any function that has an inverse. There are some weird exceptions, but they're not the kinds of exceptions that you'll see in anything before grad school math, really. Excuse me. Sorry about that. Big yawn there. I don't know about you, but I plan on going back to bed after class. So let's do another example here, though. Let's say that I told you that g of x equals 4 plus 3x cubed. And first off, I'm wondering, does this even have an inverse? So I go over to my graphing calculator, I pull it out, and it tells me that the graph looks like this. Well, I'm pretty sure that that passes the horizontal line test. No matter where I draw this horizontal line, it's only going to touch it once. So it must have an inverse. And since it has an inverse and I'm seeing it in college algebra, I'm going to assume I can find that inverse. So what I'll do is I'll set y equal to the equation. Whoops. And then I'm going to solve for x. So this time, instead of just shoes and socks, there's 3 steps I have to undo. So whatever happened last, I have to undo that first. I'm going to subtract 4 from each side. This is just like solving an equation. You already know how to do this. Next, I can divide by 3. And finally, if I want x by itself here, I need to take the cubed root of both sides. I take the cubed root of both sides, and now x is by itself. And so I'm going to call that x g inverse of y. And then I'm just going to change the name. So instead of writing g inverse of y equals cubed root of y minus 4 over 3, I'm going to write g inverse of x equals the cubed root of x minus 4 over 3. And this will be the equation for g inverse. And I mean, I can double check that. If I take, say, g of 2, that's 4 plus 3 times 2 cubed. And that's 4 plus 3 times 8 is 24. So that's 28. So that means if I take g inverse of 28, oh, that's not really visible, is it? Here, let's do purple. That means if I take g inverse of 28, I'm expecting to get 2. That's the cubed root of 28 minus 4 over 3. So since this equation is undoing this equation step by step, I should be able to watch it undo what I did here step by step. So first, 28 minus 4 is in fact 24. So there I got my 24 back. Now I'm going to divide it by 3 to get this 8 back. And now I take the cubed root, and I get my 2 back. So g inverse of 28 really is 2. This would be a pretty big coincidence if this weren't really the inverse function. So I'm going to say it doesn't prove that it's the inverse, but it's a pretty strong wink and a nudge in that direction. So this is a good way to check your work quickly, is make sure the function undoes itself. In other words, I can write what I just showed here is that I took g inverse of g of 2, and that was, in other words, g inverse of 28, and it really was 2. So I passed that part of the definition. I could pick a different number and go in the other order if I wanted, but I'm not going to spend the time right now. I don't think I need to be that paranoid. I checked it at one point. It's probably fine. Be a pretty weird coincidence if it weren't. Let me try one more function. This is going to be a somewhat more tricky one, but not too bad. It's just whatever function you have, you want to undo. So let's say that, or do you have any questions about G here? Any questions about this example? Okay. So let me go ahead and tell you, what if we had a function 3 divided by 3x plus 4? This is a weird looking function, by the way. We've taken x, we've stretched it both ways, and we've gone 4 to the left. So it's going to look something like this. It's a weird looking graph, but as a matter of fact, no matter where I draw this horizontal line, it only touches it once, so it should have an inverse. So I'm going to set y equal to the equation. And now again, I'm trying to get x by itself. If I want x alone, I need x out of the denominator. So what I'm going to do is multiply both sides by 3x minus 4. And I'll write y times 3x minus 4 is equal to 3. So since I've multiplied both sides by 3x minus 4, it's out of the denominator. Now I'm trying to get x by itself. So as a matter of fact, the next thing I'm going to do is divide both sides by y and write 3x minus 4 equals 3 divided by y. Then I can add 4. Then I can divide by 3. And that should be the inverse function. The only thing I have left to do is say, well, that was f inverse of y was 3 over y plus 4 divided by 3. And then okay. I lost myself in my notes for a second. And then I'm just going to change the name. F inverse of x equals 3 over x plus 4 divided by 3. Yeah, so that's our new function. And these two functions should undo each other. Now here's something interesting. For this function, up here, the domain was x can't be, well, it can't be 4/3, because then I'd be dividing by 0. And the range is y can't be 0. There's no way to get a 0 out of this function. It's either always going to be positive or negative. There's no way to get a 0, because the numerator isn't 0. So x can't be 4/3 and y can't be 0. That's the domain and range of the original function. But if I take a look at the inverse function, now the domain is x can't be 0. If I plug in x is 0, then I'm dividing by 0 right here. So x can't be 0. And the really weird thing is, the range of this function turns out to be y is not 4/3. 4/3 is the one number you can't get out of this formula. No matter what you plug in, you're never going to get a 4/3 out. Because if you got a 4/3 out, you would just be getting this part out, this 4 and this 3. So the only way to get out 4/3 is if this expression was 0. But this expression can't be 0. 3 over x is never equal to 0, so we can never get this 4/3 by itself. So the domain and the range have switched places, just like I said they would. So that is the science of inverse functions. That's pretty much everything to know about them. Now, I guess the other question is, why did I bring this all up? And the answer is because we've actually been studying a pair of inverse functions in particular for a couple of days now, and those are, of course, the exponents and logs. So does anyone have any questions here before I plunge back into chapter 6? If not, then I want to go, this was 3.7, and now I'm going back to 6.3. For example, 2 to the x and log base 2 of x are inverses these two functions are inverse functions of each other. They undo each other. These are opposites. Because, I mean, for example, if I said f of x equals 2 to the x, f inverse of x equals log base 2 of x, what I'm asking is these have to undo each other. So for example, if I take f of 5, I get 2 to the 5th equals 32. But if I take f inverse of 32, I get log base 2 of 32. And this is asking the question, 2 raised to what power gets me a 32? Well, of course, the answer is 5. In fact, saying these are inverse functions is exactly the same thing as saying that these are just two different ways to write the same equation. So the exponent form and the log form of the equation, in fact, the very definition of the log is the same as saying these are inverse functions of each other. So that's what we're dealing with here, is a pair of inverse functions. There's a few places we can go with this. Where do I want to go first? Do the algebra, could do the geometry. Let's do the geometry first. Here's a graph of y equals 2 to the x. As a matter of fact, this graph is pretty far up there. It's always above the x-axis. It's actually also always above this very special line for inverse functions, y equals x. I just got done telling you, if you reflect a curve over y equals x, you get the curve of the inverse, if it exists. So in this case, imagine that this blue diagonal line is a mirror, and imagine that this black curve is the function. So picture what the mirror image is going to look like. So like if 5, 32 is on this graph up here, then 32, 5 is on the green graph over here. So these are inverses of each other. This is the graph y equals log base 2 of x. So one of the reasons I was discussing inverses this morning is because that's the best way to find out what the graph of a logarithm looks like. So we can work out a few things here. Big one is the domain and range. You remember I told you I can't plug a negative number into a logarithm? We talked about that last class. We can't plug a negative number into a logarithm because there'd be no solution to the corresponding exponential equation. Well, here's another way to say we can't plug a negative number into a logarithm. Another way to say that is when I look at this graph right here, you see the domain of this green curve. It's only from the y-axis and to the right. In other words, this curve doesn't exist where x is negative, and that's just because it's a mirror image of the black curve. So as a matter of fact, another way to put that is this black curve has a domain, like 2 to the x has a domain of all real numbers, and it has a range of just positive numbers. Yes, Beyonce? Oh, okay. Welcome back. I did remember to hit record today, so you can catch what you missed. That should be up in a few hours. So what I was just saying was, since the domain and range are switching places, that's very visually apparent on this graph. 2 to the x, I can plug in any number, but I can only get a positive number out. Log of x, I can only plug a positive number in, but I can get any number out. So the domain and range really have changed places. Another thing I can see is that this logarithm graph is always increasing, and I can see that it's got an asymptote, and now instead of the asymptote being this tail out on the x-axis, like it was for 2 to the x, now the asymptote is this tail straight down on the y-axis. So if I take log base 2 of a half, that's -1, because 2 to the -1 is a half. If I take log base 2 of a quarter, that's -2, because 2 to the -2 is a quarter. If I take the log of 1/8, I get -3. If I take the log of 1/16, I get -4, and then -5 and -6. So the closer I get to 0, the faster I'm zooming down and down toward -infinity with the y. So this is a strange function that once you get past... Oh, here's another thing before I say that next sentence. I know that this is the point 0, 1. The reason I know that is 2 to the 0 is 1. Anything to the 0 power is 1. So 0, 1 is going to be on this graph and any other graph, like 3 to the x, 5 to the x, e to the x. Well, that means that over here has to be the point 1, 0, since I know that the x and y coordinates switch places. And that's like we said yesterday. It's a true statement that no matter what the base is, log of 1 is 0, because anything to the 0 power is 1. So that's another way to think of that. You can think of that as a fact about the definition, or you can think about it as a fact about the geometry of inverse functions. Since the definition is equivalent to them being inverse functions, those two ways of thinking get you the same results, but with two different thought processes. Whenever that's the case in mathematics, whenever you can use two completely different thought processes to arrive at the same answer, first off, it's really cool because that doesn't happen in most other subjects. And second, that means it really pays to understand both processes well, because if you do, then you can see the symmetry between them through that connection. And being able to directly perceive that symmetry is a huge part of the deep understanding of mathematics. That's kind of pro mode, is you want to, if you can see why the two things are symmetric, why knowledge in one directly corresponds to knowledge in the other realm, you've really pierced the veil and peeled back a lot of the surface syntax to get at the deep semantics of what's going on. So that's, in my opinion, that's one of the most that's one of the deepest things about this subject, is the way that it very directly connects the definition of log notation to the idea of inverse functions in a way that, in my opinion, if you understand one, you understand the other. So I think that connection really illuminates both what a logarithm is and how inverse functions work. So that's why I'm teaching it both ways. Let's see. So we've got the graph of a logarithm here, and that's what that looks like. And that's visually showing us what we understood geometrically before, is that you can't take the log of a negative number. The other thing I want to do is a little bit of algebra for these log functions. Let's see here. Oh, I know what I want to do. I want to make a table. Our 4 basic log properties. Properties is in attributes, not as in real estate. Yesterday we discovered, or you know what I mean, last class we discovered, excuse me, last class we discovered that log base b of 1 is equal to 0. And that corresponds to the exponent fact that b to the 0 is always 1. we discovered that log base b of b is 1, because that corresponds to the exponent fact b to the 1 equals b. And now I have two more facts based on the fact that these two functions are inverses. If I take b to the x and I plug it into log base b, so if I take log base b of b to the x, this is going to be x. And the reason for that is I'm saying, what power do I have to take b up to get b to the x? The answer is, if I take b to the x power, I have b to the x. It really feels like a tautology when I put it like that, but it feels a lot more meaningful if I say, well, I take the function and I plug it into its inverse function. These two functions are inverses of each other, so they undo each other and I just get my input back. If I say it that way, it feels really meaningful, but if I say b to the x power is b to the x power, then it feels simple and stupid. So it's really just a matter of looking at things, and that's why I think that symmetry is so important, is something that feels profound and elusive in one mode of analysis feels elementary in the other mode. It's like the end point of one mode analysis, but it's the start point of the other mode of analysis. So we can't really think of mathematics as having a defined beginning and end. It only has routes you travel from one piece of information to another. And your start point might be my end point, but we'll meet in the middle because math is consistent. I don't know. There's probably a lot that you could infer from that, a lot of deep stuff, but I'll leave that to kind of mull over for you. If I'm thinking of this as plug a function into its inverse function, they cancel out and only the input remains, then of course I should be able to do that in the other order too. Since inverse functions come in pairs, I could say, if I take the exponential function and I plug in the logarithmic function, I should just get the input back. The other way I can think of that, of course, is I could say log base b of x is saying, what power do I have to take b to get up to x? And this is the answer. This is the power I have to take b to get up to x. So if I go ahead and do it, the madman, if I take b up to that power, I do get x, because that's the definition of the logarithm. If I take b up to this power, this is the power that says take b up to the power and you get x. So I do get x. I know that that was a kind of twisty sentence, but if you think about it in terms of inverse functions, this one isn't actually that bad. So these are both from inverses. Which means if I say something like, I want to know what is log base 10 of 1,000, I could say, well, I know 1,000 is 10 cubed. And then I can say, these two functions, 10 to the x and log base 10 of x, they undo each other. And so I know that my answer is just going to be 3. Otherwise, I'd be saying 10 to the third power equals 1,000, so log base 10 of 1,000 is 3. Either mode of analysis works here. And if I take the log base 2 of 1,024, which is 2 to the 10th, I know the answer just has to be 10, because 2 to the 10th power is 2 to the 10th power. If I take if I take 3 to the power of log base 3 of 9, if we didn't know these facts over here about inverses, we could still muddle our way through this. I'd say, well, log base 3 of 9 is 2, because these two switch places. 3 squared equals 9. So since those are both true, this has the same thing as 3 squared. Well, of course, that's 9. But if I knew this fact, then it would be a little easier. I'd say, oh, I took 9, I plugged it into the log, and then I plugged it into its exponent. Those two functions cancel each other, and I just get my input 9 back. So now I don't have to do this step, because I know what's going to happen. So I want you to be able to think of it both way. And the advantages of that is then if I say what's 3 to the power of log base 3 of 7, you could just say the answer is 7, because these two functions undo each other. Otherwise, you'd have to say something like, well, this number here, log base 3 of 7, it's about equal to 2.3, but it's the number, or 1.3 rather, but it's the number where if I take 3 to this power, I get 7. So when I took 3 to this power, I did indeed get 7. I like the inverse functions understanding of it. It's a little bit easier. Let's see. Here's one other trick we can do with this method. If I take, I know that 2 is equal to e to the power of the natural log of 2. And that's because natural log is log base e. So these two functions undo each other. E to the natural log, just like 3 to the log base 3 of 7 is 7, e to the natural log, the log base c of 2, has to be 2. But a really cool trick this gets us is then if I have 2 to the x, that's equal to e to the power of log 2 to the x, which is nested exponents, so I can multiply the exponents. It's e to the power of log of 2 times x. This trick is going to come in really handy in section 6.6. Because what this trick does is I had some random exponential function, the base happened to be 2, but I turned it into an exponential function whose base was e. And like I told you before, e is that special number where e to the x is its own slope. So if I have the exponential function written in terms of e, what that gets me is easy calculus later. So scientists like to put their exponential functions in this form instead of in this form because it makes their calculus easier. So we're going to practice doing that, but that's coming next week. One more thing I want to say is, remember last class I told you if b, want that in black, if b to the x equals y, then log base b of y equals x. The base stays put, the input and the argument switch places. Well, another way to remember this now is you can still think the base stays put, the input and the argument switch places, and that's a perfectly good way to think of it. I like it. So the base stays put, the input and the argument switch places. But another way you can think of it is that these are inverse functions. So if my output from b to the x is y, then if I plug that into the inverse, I get my input back. So the input and the output of these two functions have changed places. If you think of these as functions now, it's just the input and output have changed places, like an inverse function does. The inverse and output change places. It changes the x and y coordinates around. That's why it mirrors over that blue dotted line y equals x. So that's a second way to think of how to remember to switch between exponent form and logarithm form. It's two of the same thing. So when we get back on Thursday, what we're going to do is we found these 4 basic log properties yesterday and today. But what I want to do now is, just like we did in Unit 1, we came up with this really simple definition that exponents are repeated multiplication. And I said we can derive all kinds of really cool advanced knowledge just from the fact that we want this definition to stay true. It's going to restrict what exponents can do in really neat ways. Well, if exponents were neat, then logarithms are super duper neat. In other words, just the fact that I've made this definition that the input and output change places, this is just the definition of the logarithm here again, but it's going to get us to some really amazing stuff. So that's what we're going to do next class. We're going to explore some advanced implications, and the way I'll do it is I'll write a fact about exponents that we learned, like a fact about exponents we learned is that if I have 4 to the x times 4 to the y, I get 4 to the power of x plus y. So multiplication outside turned into addition inside. It turns out that logs are going to go backwards. If you have multiplication inside a log, it'll make addition outside the log. So here's an example of that. Here's a sneak preview of the next class before we leave, since we do have 5 more minutes. Yeah. Log base 6 of 3. Should have grabbed my calculator before I started. But let's see, log base 6 of 3. It turns out to be about, and now this is an irrational number. It goes on forever without repeating, just like the square root of 2, just like pi. It's about equal to 0.6131. Now, whoops, turned my calculator off. There we go. Log base 6 of 2 is about equal to 0.3869. Okay. I'm not just quoting random logarithms at you. There is a method to the things I've just written down. And what that is if I add these two numbers together, 9 plus 1 is 0, carry the 1. 1 plus 3 plus 6 is 0, carry the 1. 1 plus 1 plus 8 is 10, so carry the 1. 1 plus 3 plus 6 is 10, carry the 1. So somehow I'm getting 1. And now I've only written down 4 digits. These go on forever. But even if I wrote 10 or 20 or 50 digits, I would still be getting exactly 1. Because it turns out that this isn't an approximate thing. This isn't a crazy coincidence. This is an actual truth of mathematics. Log base 6 of 3, even though these are both these weird irrational numbers that we can't describe any other way, if I add them together, I get 1. And it doesn't feel like it should be the case, you know, these two weird numbers. But well, let's work out what has to be the case here. Log base 6 of 3 plus log base 6 of 2. If I just say this is some number x, and I already know that x is very, very close to 1, but I want to prove that it's exactly 1. If I have this equation, okay, I can take 6 to the power of each side. Bear with me here. What this gets us is, if I have two numbers added together, like no matter what those numbers are, if I say I have 6 to the power of a plus b, we know from chapter 1 that that's 6 to the a times 6 to the b. So I'm going to do that transformation here. This is 6 to the log base 6 of 3 times 6 to the log base 6 of 2. Well, what I know is that this number right here, I took a 3, I plugged it into the logarithm and then into the exponent. They have the same base, so they cancel out. They're inverse functions, log base 6 of x and 6 to the x. If these two functions cancel out, I'm just left with the input, which is 3. And if these two functions cancel out, I'm just left with the input, which is 2. So 3 times 2 is 6 to the x, but of course that means 6 is 6 to the x. And the only thing that x can be then is 1. So it's weird, but what we found out is since 3 times 2 is 6, since 3 times 2 is 6, I multiplied them on the outside. If I take their logarithms, base 6, and add them together, I get 1. We're going to explore why this works in the next lesson. So that's where I want to end things today. That's a sneak preview of next classes. We're going to learn 4 new properties called the advanced log properties, and this idea that addition outside changes to multiplication inside is one of those 4 properties. All right, that's all for today. I will see you all on Thursday.